When we talk about multiplexing in a shared environment, we can look at the multiplexing scenario as a single communication link, or it could be a federation of intermediate switches and routers and maybe even gateways. It means that whatever we are looking at, we are trying to assess how efficient is multiplexing and how much cost is incurred. Therefore, in this module, we shall try to understand what are the well-known multiplexing techniques. It would just be an overview. What is the capacity overhead in a very generalized way? And if we move from strict kind of multiplexing sense to flexible kind of multiplexing, what is the performance gain that we achieve there? These two figures show the most well-known types of multiplexing, namely the time division multiplexing and the frequency division multiplexing. Here you can see that if there are 6 time slots in time division multiplexing, and if half of the time slots are unoccupied, it means the user is not active and is not generating data in its respective time slot. What do we get? We get these empty slots not being occupied by anybody else, causing wastage of resources. Similarly, in frequency division multiplexing, if each user is allocated a frequency spectrum band, and if that band goes unutilized, the overall system suffers from inefficiency and underutilization. These two examples can also be analogous to the core division multiplexing and the space division multiplexing scenarios as well. So it means there's always a need to think about multiplexing in such a way that the resources are dynamically allocated to the users which are active and deallocated from the users which are not active. So when we talk about the notion of allocation and deallocation in a dynamic way, we are actually introducing the overhead. This multiplexing overhead adds additional capacity requirements, and this is termed as the capacity overhead rho. It is actually defined as a ratio of the difference of the practical resource allocation to the optimal resource allocation and the optimal resource allocation, represented in percentage. The optimal resource allocation is actually the close to perfect resource allocation for an application I, and the practical resource allocation to an application I is what can be done in a real world scenario. So you see, this expression is a good understanding of how the practical and optimal resource allocations are related to each other. In case the practical allocation is as good as the perfect optimal resource allocation, the capacity overhead is going to turn out to be 0. And it is going to reach a maximum value if the difference between the practical and the optimal resource allocations is higher. Let's get back to our initial assertion that we should have the capability to allocate and deallocate multiplexed resources amongst a number of users in a dynamic way. That is, in scientific terms, called statistical or packet multiplexing. As an example, let's say there are n users and all of these users are sharing a single communication channel. Specifically, we can think about a scenario where there are 10 users. Each user is generating 100 kilobits per second worth of data when it is active, but it is only active 10% of the time. So it means 90% of the time it would not be active, and its resource allocation would go wasted if it is done in a strict multiplexing sense. So with statistical multiplexing, it has been observed, and you can even compute that a total of 35 users could be accommodated, and the probability that more than 10 users are active at the same time turns out to be 0.0004. It means the probability is close to 0. What we understand is that we can allocate a system of strict multiplexing that can afford only 10 users to accommodate 35 users, and the users wouldn't find the network much occupied and would have the chance to get their data delivered, because the probability that all the users are active all the time gets to be very low.